Hello, and welcome to the second part of the MI Knowledge Campaign, where we're going to learn about artificial intelligence and machine learning today. So I'm Ricky Schwartz. I'm the head of Innovation, Automation and Tools, and Machine Intelligence for Managed Services for North America. And today I have Jay Samuel with me. You want to introduce yourself, Jay?
Yes, I'm Jay Samuel. I am a data scientist in Managed Services.
Okay, great. So thanks for joining. I thought we'd start with trying to understand what the difference between automation and artificial intelligence and machine learning is. I think that sometimes these words get used interchangeably, and I think it's important to understand the difference between it. So as you see here on the slide, very simply put, automation basically augments our current ways of working, and so it's similar to our current ways of working. It just lets us do our work more efficiently, with less errors. So artificial intelligence and machine learning, that's when you want to do something that's beyond human capabilities. It's sort of a new way of working. So new insights, it's the human brain can't handle as much data as we have to process. So we use artificial intelligence and machine learning to help us with that. So I think we saw this slide last time, and we talked about it a little bit, the types of automation and the automation journey that we're on. And we talked about, on my left side, automation, and on the right side is our machine intelligence. So I think it's important to understand that automation and machine intelligence, they go hand in hand. And I'll show a little bit more about that in the next slide or two. But again, what's really exciting about this slide and what we're trying to show here is the intersection between automation and machine intelligence. So what we're seeing typically in the market is these machine intelligence solutions and algorithms. They normally just spit out a prediction or they give you an insight, but they don't execute or act on that insight. But what we've been able to do is integrate one of our automation platforms with one of our machine learning algorithms, and we've been able to execute on the insights that come out of those algorithms. So this slide is really sort of meant to show you more in a very simplistic fashion about how automation, artificial intelligence, and machine learning fit together. So what you can see is that automation is the general sort of category, and that also includes robotics process automation and runbook automation, which is what we talked about in the last webinar, if you recall. So artificial intelligence is a subset of automation, and then machine learning is actually a subset of artificial intelligence. So Jay and I will get into the differences of that in a moment. But first, I think it's really important to understand why do we need to incorporate and use automation and artificial intelligence and machine learning. So this is a simple slide, and the point of the slide is to show you that as the number of devices exponentially increases, our operating expenses increase as well. So in order to offset that, we need to augment, or we need to offset that cost with new technologies and new solutions like automation, artificial intelligence, machine learning, AR, VR, right? So that's kind of the point here, is to show that as data and as complexity in the networks increase, the operating expenses also increase exponentially, and we need to offset it with these new technologies. So this is sort of to show you how much data that we're talking about and the short amount of time it's going to take until we get to these 22,000 terabytes of data, right? So we need to start looking at AI and ML today so that we can handle this amount of data. And what we'll talk about shortly in the next couple of slides is how artificial intelligence really is meant to replicate what the brain does, but the brain can't handle 22,000 terabytes of data. So what is artificial intelligence? So artificial intelligence is a field within computer science that, as I said, basically seeks to emulate the human brain. And that's pretty much it. It's pretty broad. And some areas, for example, are natural language processing, computer vision, virtual agents, problem solving, machine learning, which I'll talk about in the next slide, and advanced robotics. And in Ericsson, in the next webinar, you'll see that we are working in a lot of these different areas, like natural language processing, computer vision, machine learning, et cetera, et cetera. So what is machine learning? So machine learning is really algorithms that continuously learn from data. And what you can see on this slide is in the traditional programming, we input data, we tell the program what to do, and then there's an output. But what you see in machine learning is that we feed the output back into the computer so that it learns and it executes more efficiently. Jay, do you
So
wanna add
yeah,
anything?
and I'd just like to add what's interesting is in a traditional computer program, you give the rules in the form of an algorithm or whatever it might be, and you have data input, you have the program that runs, and you get an output. In machine learning, many times we are working with multidimensional space, and we really cannot comprehend the rules. So we let the data actually dictate what the rule should be, and then have the output reinforce that and have these algorithms that learn. And later on in the presentation, I'll talk a little bit about these different algorithms, and we'll illustrate with very simple examples in our context.
Okay, good.
Go ahead.
Thanks, Jay. So what is machine intelligence? Because I think that that's a buzzword that a lot of people are hearing around Ericsson. So machine intelligence is an Ericsson coined term, and basically what it means is it's a combination of machine learning and artificial intelligence. Keep it simple. So what types of machine learning are there? Well, there's 3 different types. There's supervised learning, there's unsupervised learning, and there's reinforcement learning. So what are the differences between them? Well, supervised learning is where you actually label the data. So the data is the big thing here when it comes to machine learning and artificial intelligence. As I showed on the previous slide, there's 22,000 terabytes of data. So what do data scientists do? And Jay's a data scientist, so he can explain it in more detail. But they basically take that data, they structure it, they format it, and for supervised learning, they label it. And so then you put the data into the algorithm, so the algorithm can ingest the data, and then the algorithm does what it's supposed to do based on the data that you labeled, right? So next is unsupervised learning. Now this is when you don't label the data and you just send the data straight to the algorithm. You still need to format it and structure it, but it's effectively when you just send the data to the algorithm. So if I'm going to give you an example of the difference between these two, I'll use pictures of cats as an example. So for supervised learning, you get a chunk of data, and when Jay's doing his work, for example, he would label this data as a cat. And then what would happen is you would put the data into the algorithm, and it would know that this data is a cat, right? For unsupervised learning, you just put in pictures, and the algorithm doesn't know whether it's a cat or a dog or whatnot, but it learns over time. And we'll get into a few more details on that in the next slide. So supervised learning is labeled data, unsupervised learning is unlabeled data. And then there's reinforcement learning. So reinforcement learning is all about reinforcing an action that occurred through positive or negative rewards. So if you put something into the algorithm and it does X, and that's a good thing, then you positively reward it, and it knows every time that you put whatever it is into the algorithm, choose X, right? But if you choose path Y, then that's something you don't want it to do, then you get a negative reward, and then the algorithm doesn't go down that path anymore. So that's essentially what different types of machine learning. Okay, so next are problem types for machine learning. So under supervised learning, you have classification and regression, and these aren't the only ones. There's quite a few other ones as well under both supervised and unsupervised. However, Jay will get into some of the challenges later, and that's one of the challenges. But as an example of a supervised learning, you label the data as a cat or a dog, and then you put the data into the algorithm, and it classifies it into cat or dog, right? And then from a regression standpoint, that's another algorithm that basically just tries to best fit to be able to predict what's next. So you have a set of data that's labeled, and then you create a line that you want to try to fit that data, and then based on that line, you predict what comes next. So that's effectively what regression is. So unsupervised learning, remember, is unlabeled data, and so one algorithm we can use is clustering. So you can see here on the slides where you get data that tends to cluster. But what happens is you don't know what that data is, so a data scientist, for example, would need to go in and look at the clusters and give some context to it. And then there's anomaly detection. So this one is very important from a managed services standpoint, which is where Jay and I work. And so basically what this is being able to predict anomalies in the network and prevent it before it occurs. So effectively what you have is we have these thresholds that are set, and then the network ends up working sort of within the thresholds. And then if we see that the network is going like this to go outside of the threshold, we want to predict when that's going to happen and then proactively prevent it. Another algorithm that we're testing in managed services is to automatically set those thresholds. So for example, if there's something like seasonality, where we know that the thresholds typically change, then we want the algorithm to automatically change the thresholds so that we don't get alarms when the network is going to breach the threshold. So that's pretty important from an anomaly detection standpoint in managed services. Jay, is there anything you want to add before we move on to yours?
No, we'll see some examples of this in the context of Ericsson, where it'll become a little bit more clear. And if there are any questions online, can we take them now?
We can get to those at the end.
Sure, great.
So I think...
Sure.
Go ahead.
Thank you, Ricky. So let me see.
There you go.
So let me paint a very simple example from a process perspective, and then we'll work our way from there to understand some of these algorithms. So in this slide here, I have a very simple business process. Some of this applies to Ericsson in the managed services and customer network support group. So you have a customer, they have an incident, they'll open a case, somehow that case will find its way to an engineer. Let's call that engineer a tier 1 engineer. So there are a couple of ways that the case could be resolved. It could be resolved by the tier 1 engineer with a final resolution that you see in the arrow that's on top, or the tier 1 engineer might require some help or needs to go to a PDU team. In which case, they would send the case over, the PDU team would work on it and get back with a response, and then eventually the customer will get their final response. Now, with this very simple process, I have written up a few lines of records of data with some columns. So here, let's start looking at the data in the table. From the second column, you've got a severity, you have a node in which the case was opened, and the number of hours that were spent by Ericsson in resolving this case. And in the first column, we have some very interesting information. For each of these cases, we already know whether a PDU resource was consulted or not, or engaged or not. So with this as a backdrop, let's look at some of these machine learning algorithms. So in this first, right on top, if you see, I have the data listed out. Now, when you look at this data and digest it, we can very easily see that every time the severity is high, the PDU team is engaged. And we represent that piece of information by putting it into that tree, which is nothing but a simple decision tree. So we have severity as a node. If it's high, then we know PDU has been engaged in all of those times that the severity was high. And on the left side, if it's medium, we need a little bit more information before we can decide whether this case needed PDU support or not, which is an MSC node or an RBS node. So what I've described to you here is a simple decision tree based on the information in these 4 lines of data that we have. Now let us say a fifth case comes along with one of these characteristics. So we'll first test the severity, see if it's medium or high, and if it is high, we'll classify this new incoming case as something that would likely need PDU engagement based on past data. So this is a very simple decision tree, and this is how the decision tree is built and used. Now, as simple as this is, imagine with me higher dimensions. Here we have just used 2 dimensions of severity and node. If we increase these dimensions to say 3, 4, 5, 8, or 10, first of all, we cannot draw it and depict it in a diagram like this. And secondly, the outcome would be very, very difficult for a human to imagine or come up by intuition. And that's where these algorithms show their power and how they can help us make these decisions. So in 10 dimensions, say, a new case comes in, the algorithm will be able to tell us into what bucket it is classified, whether it needs a PDU support based on previous data or it does not need. Okay, so I hope this gives you a small window into how decision trees are constructed.
Jay, let me just make a quick point
Sure.
there. I think that this is a really good point that you're making, and the reason why is because this is a very simple situation. It's a very simple problem, and sometimes we just use automation for this problem. You know, typical maybe runbook or robotics process automation we can use on something simple like this. So we shouldn't just run to use AI and ML, you know, just because.
Yeah,
right? We should
exactly.
use it where it makes sense, where there's a high number of variables. The more variables you add, the more combinations of outcomes there can be until the human brain just can't handle it, and that's why we need AI and ML.
Yeah, absolutely. And now let's take it a notch up. Now let us say instead of classifying, you want to know the likelihood of a case going to PDU or not. So here we have got like deterministic outcomes, like either it goes to PDU or it doesn't. But then there are certain cases that do, certain that don't, certain possibly could have gone, but they didn't. So let us say we want some sort of a probability. That's when we start looking at another algorithm, which I'll describe to you, which is logistic regression. Now let us say we take each of these cases as a data point and plot them in three-dimensional space. 3 dimensions because we have got 3 columns in our data. And these cases will be pretty much scattered in 3-dimensional space. Then what we can do, depending on whether each case is engaging PDU or not, we could introduce a plane, which is shown in this diagram, called a discriminator plane, and use that plane to move it up and down, tilt it back and forth, to divide the set of cases into either those that require PDU help and those that don't. Now, depending on the distance of each of these cases from this discriminator plane, we could come up with a probability of the case needing PDU help, engaging PDU or not. So if a data point or a case is far away from this plane, discriminator plane, then very likely it is one category or the other. It might need PDU to engage PDU or not. If it's very close to this discriminator plane, it could fall on either side of the plane. So the probability of engaging PDU is very low. So this is a good example where it is not a clear yes or no answer or a clear classification, but more of a probability. Now, based on this, we can make several more different kinds of decisions. And finally, again, we can imagine all this and understand because it's in 3-dimensional space. We as human beings can still think in that space. But if you increase this to multiple dimensions, we really can't show it on a diagram, but the algorithm will be able to give us. Yeah. So anything to add there, Ricky?
I think this is another good example to tie it back to where I said that we're at the intersection between automation and machine intelligence. And the reason why I say that is because let's say the farther away from the plane, as you said, means that we more than likely a higher probability that we will engage with the PDU. So that's what it will tell us. High probability of this incident or ticket, we need to go engage with the PDU. Now we can integrate our automation solution and we can actually send that ticket to the PDU without us even touching it. So that's where I'm saying that automation and machine intelligence really go hand in hand.
Absolutely. So now let me transition quickly to the unsupervised learning algorithm. Now, Ricky had told us about labeled and unlabeled data. So here we have the same data. I've added the 4th column back in, which is end-to-end hours. And let us say we were just plotting the nodes on the y-axis, the RBS and the MSE, and the number of hours spent in each case on the x-axis. Now, I've just simulated some clusters. I'm not saying this is how the data actually looked. But let us say in the simulation, we find clusters around a low end-to-end hours or hours put on the case on one side, on the left side. And on the right side, let us say there are cases clustered which have a lot of hours against them. Now, once we see such patterns, that is when we as managers can come in and see what similarity exists in each of these clusters. Now, it's possible, and I'm just speculating and simulating here, it's possible that the low number of hours on these cases are typically cases that were sent to a PDU or a different team was engaged. It's possible that is a team with more experience on the product itself, not necessarily the customer, and they could probably knock out these cases at a lower number of hours. Whereas the cases that have a higher number of hours against them are probably very specific to certain customer configurations, which only specialists like the Tier 1 teams can handle. So such insights can emerge from clustering types of algorithms. Now, I want to emphasize again, we are talking two-dimensional space. We can see and reason with these clusters. But in reality, we will have multiple dimensions, and we really can't see them, but the algorithms will be able to tell us about these clusters. Anything to add there, Ricky?
No, I would just say that this is a good example to show the power of AI and ML, because it really shows you how can we best utilize our resources, right? I mean, it tells you that you know, we really need PDU resources to focus here, as opposed to focusing here, where maybe the Tier 1 can handle the issue instead of a PDU. So that's sort of the practical example of how we can use this technology.
Those are some of those decisions that we would have not been able to do ourselves as managers, but we can use this algorithm to guide us.
Yes, exactly.
Finally, I'd like to go over some of the challenges when using these kinds of new technologies in our space. So first is there are so many KPIs. In other words, there are so much of data, different kinds of data that we have to solve our problems. What do we choose? What do we use? So one guiding principle in this area is let the business question drive the data. So the business question is absolutely essential. And we as managers, we as SMEs in Ericsson and in our domain are the ones who can come up with these business questions, such as I want to reduce turnaround time by a certain percentage, things like that. We have got different data formats. That is also adds a level of complexity. Again, use business question to drive what kind of formats you want to use, what kind of formats you want to normalize into. And the third item is there are so many machine learning algorithms. I mean, right here, Ricky and I have talked about like 4 or 5 of them. We've got 3 different classes. There are more. Which ones do we use? Which ones are the best? There is no best machine learning algorithm the way I've stated it. Let your business question drive what methodology you want to use. As a very simple example, we talked about classification algorithms, yes or no, very deterministic like. And then there are algorithms like logistic regression that help us with decisions that are probabilistic in nature, you know, high probability to belong to a certain class. And your business question will drive what kind of algorithms that you would use. And finally, we in Ericsson have something that the researchers don't have, which is the real world. So we can implement these algorithms, we can test them, we can deploy them, and we collect data. And we can see if they're working, and we can fine-tune our algorithms further or change algorithms if we have to. So we should use all these tools to overcome these challenges that I've listed out. I've just listed out some of the common challenges that we encounter. I'm sure there are many more which are more specific to your particular business problem.
Yeah, I mean, what I really want to highlight here, though, and maybe as a common thread through all of this, is if you go back to the data, the growth of the data, the 22,000 terabytes. One is we need this technology to be able to handle that. But the other thing is the data is the real gold in this, right? I mean, so it's really important to have lots of data, and it's important to have the data, you know, in a structured format. So for all of you out there who are inputting data and who are collecting data, this is why we need it in a structured format. It makes Jay's job a lot easier as a data scientist when he's trying to structure and format the data. And we are using tools to help identify gaps in data and where we need to improve, and et cetera, but the data is the real gold here. And this is why Ericsson can really capitalize on this, because we sit on a wealth of data.